Okay, physics dorks. It's time to see if we can. It's time to see if we can get a good explanation or just an overview explanation of the video was that I sent you yesterday. Hopefully, it made sense to you. But I'm just going to walk through a couple of things about series and parallel circuits so we can do a lab with these two. And quite literally, kids, it's kind of weird, but we are right on track where we normally would be in the school year, and we're doing kind of the same things we would have in class, just albeit on a computer. So anyway, series and parallel circuits, the idea, as we said before, or as it says in the video, you've got just what they talked about before. You've got some sort of charge pump. You got resistors, these little squiggly things right here, okay, and there's your circuit. Now, the idea with a series circuit is that everything is in a line. You see how it goes like that? Boom, 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 boom. The current has to flow through all of them at the same time. Now, think about that. I always look at it kind of like a garden hose trying to run something, or even a river trying to run, let's say, a dam or turbine wheels or something like that. The more you put on there, the more it's going to slow it down. So what I always did with an analogy in class was this kind of idea here, where I always came up with something called a stream down a mountain concept. So what I would do is I got an arrow here showing the top of the mountain and the bottom of the mountain. And if I draw a really, really bad picture here of a mountaintop or whatever, and there's snow up at the top, okay, the water is going to flow down through a stream all the way down from that snow all the way down the river. See the current going with the white arrow right there. Okay, now what you have is the top of the mountain to the bottom of the mountain. You've got your potential, your volts of electricity. So the higher the mountain, the more potential. The higher the voltage, the more the potential. Now, the thing is, that water, it's up at the top, like, woo, I got this whole distance to go down. Yay, I'm going to just cruise. And suddenly, right in here, I put some sort of impediment. I put some sort of water wheel right here that slows the water down. It's like, oh, crap, I got to do some work. So it gets slowed down again. So it only technically gets to fall from here to that first wheel. Okay, you're like, okay, it's slowed down a little bit. But the idea is that it fell. Let's say this is a total of 100 feet here. Let's say it fell 33.3 feet right to here. Okay. All right. So the water kind of stopped. It's got to start all over again until it goes all the way down here, another 33.3 feet to this point right here to another water wheel. And so at that point, boom, it hits another one. Oh, dang it. I got to start all over again. But again, it fell 33 feet. Okay. Long story short, you put one down here at the bottom. I don't know if you can see that. I got to switch a little bit. You put one way down at the bottom. You got another water wheel here. Well, and it slows it down one more time. The idea is that when you put everything in a series like this, that current is slow down, and the voltage is, well, it is all added up together. It's not an efficient way to actually run your system, okay, because it slows down, but it's very, very simple. Okay, and let me erase this quick with my cotton ball and rubbing alcohol. Oh, God, I thought it wasn't going to come off. My wife would freak. Hold on, kids, 1 second here. All right, so now if we go take a look at the idea behind all this, was that the total voltage drop is equal to the drop at each of the resistors. So if it fell 33 feet to each one of them, 33.3, it would end up being 100 feet total, okay? So all of them add up to the total voltage. And the resistance, you just add up all the resistors. So if you got 3 resistors, 3 water wheels, they all go together to sort of slow the whole darn thing down. That's a series circuit. We don't use those in our house because, well, the more, let's say you plugged in more stuff in your house, what would happen to the amount of current going through everything? It would slow down. The more lights you'd plug in, the dimmer it would get. The more lights you plug in, the dimmer it would get. Okay, you following? Because everything has to go in the same direction through one of them. So the other option is something called parallel. Okay, now in a parallel circuit, you can see this here. With a parallel circuit, now you've got your power source, but now you bring it up here. Okay, you know another way of looking at this? It's kind of like a water park. If you go back here on that picture here, let's say it's a water park and this is that one of those slides. Everybody's got to wait. Oh, here's the fun part. Oh, here's the fun part. And everybody's got to stand right here and wait, all in line. You got to go, and then it slows the whole system down. But if you do a parallel system, Look at this. Here's the top of the water park slide or whatever else. You get up to the top, and they say, okay, you go down tube number 1, you go down tube number 2, you go to 3, 4, whatever else. How fast could you get people to go through there? Okay, and all of them get to slide down the whole distance the entire way. You know, that's a really tall water park. Everybody gets the same ride no matter which one they go on. You get that? And then they can really cruise through it. Now, the same thing with water. If we had water or electricity, what you're doing here is you're giving multiple pathways for all those things to go through. Now, a couple things go on with that. What's really cool about it is that you can make all those resistors have all the voltage they normally would have. So it's kind of the same way we go back to our mountain picture right here. Okay, if I do a little analogy, here's that really bad picture of them. Oh, there's still acetone on there or whatever else. Not drawing that well. Yeah, there's your mountain. There's your snow at the top. And now the water, it has 3 pathways to go. Okay. And so now it can split, and you've got one down the middle like this. And then you've got like this. And check it out. So now what can happen is that water, technically, all of it gets to fall from here all the way down to the bottom. Okay? So the water is not impeded at all until it gets to the very bottom. So that water wheel gets to do a ton of work, you know, because it has that whole distance to fall compared to a series where it's slow down, slow down, slow down. Now, the only problem is to feed all those, you better have a lot of water up here to feed all those systems. Making that analogy to electricity, going back to this other picture here, you better have a crap load of electricity to feed all these resistors. And what happens if you keep adding resistors? So what do you need more? You need more electricity. Well, what did we learn in the unit before? What can massive amount of current do to a resistor? A wire? It could heat it up. So if we keep adding resistors all the way off to the top here, what happens to the wires in your house? Eventually they can get hot. That's why there are building codes to how many light bulbs you can add. Okay. So a couple of also rules with that. We take a look here. Where's my acetone or my rubbing alcohol? Go on, get off of there, stupid thing. So the key to all of this, though, as it says at the top, the voltage drop is the same for all resistors. So it's really cool. So if you have a 110 volt system in your house, every single appliance gets 110 volts. Okay. All the same, all the light bulbs on your Christmas tree, everything all light up the same. Doesn't matter how many you add. The only problem is if you keep adding up, eventually you're going to have too much going in. It's going to heat up and be an issue. Okay. And they have the same current they would if they were all alone. So the current, though, here's the problem. So you add up, it's got the current that would have alone. You add up 1 current, 2 current, 3 current, and you get a total. So you keep adding up current. Eventually, so much current, your wires get hot. Okay. Equivalent resistance, it's a little bit more tricky to talk about, but it's weird. The more resistors you add, the less resistance the current feels. Why is that? It's like, again, at the water park. Let's say you go in line and they have 2 slides open. So, okay, everybody's got to wait in line a little bit because there's 2 slides that are open and it goes fairly quick. Now they open a third one. Ooh, how quick do you get to go through? There's less resistance. Oh, I'm going faster. Suddenly they open up all 10 water slides at the top. You can literally run up the stairs, run to the next water slide and go down. The more resistance you add, okay, the more places you can do stuff, the less it actually feels. And the problem is people are going to trip up the stairs because they're running up the stairs. They're going to get issues. The current's going down the wire like crazy. It's going so fast, it's heating up. So the problem is with that much, lowered resistance, you can run into problems. Okay. All right. So those are the basics. Hopefully that helped to, explain a little bit about series and parallel. And what we're going to do with this is tomorrow, we're going to use that same basic lab thing we did the other week with Ohm's Law. Really cool thing. And it's really kind of cool. We're just going to add together resistors and run through series and parallel. And you will see the difference. It's really cool. Okay. All right. Hopefully this makes sense. Later.